I will introduce first what the problem statement is, why is it relevant for formal modeling, why formal modeling is required at all, and then describe our approach, which combines two different methods. And then I will describe our own contributions specifically related to that and summarize. Before I go to the problem statement, so I want to say that I would like it to be more interactive. So at any point of time, if you want it some clarification, because there are some hardware related topics which are involved, attestation, Intel TDX, ARM CC, and so on, some technologies, abbreviations, and many, many things. So if you feel confused at any point of time, I would be very happy to clarify that. So feel free to interrupt. It's not going to be like just me talking. I would be very happy to be interrupted. The field of confidential computing itself, there is no formal definition so far for the field. It's emerging, and people have used it in many different ways and many different meanings and so on. So the way I would like to present it is that we have one relying party, and it would like to upload its workload or application to the cloud or to some third-party infrastructure where it has lesser control than its own machine. And what that means is that below that application, there would be some software layer that would be like, let's say, some OS, which will be controlling or running that application. And underneath that, there has to be a hardware and a software, a hardware and firmware, sorry, which would be actually controlling and running that software, OS and so on, so everything. So all of this combined with the cloud provider, which is in control of everything, now comes the question of the threat model, what exactly the threat model is for this specific scenario. That I want to upload my application to the cloud, and I still want to have some guarantees for security so that I am in control of my data and application. The idea here is that, or the aim of confidential computing is to remove this cloud provider from the trusted computing base. That's the core aim of confidential computing. It has not yet achieved it completely, but it's trying to achieve, let's say, the goal or the long-term aim of that is basically this. So there are three main parties in the confidential computing scenario. So there is this cloud provider. This, as I said, we want to remove this from the trusted computing base. It can be, let's say, IBM or Google or any Alibaba and so on. On the software side, or let's first talk about the hardware side. There are different providers providing different kind of solutions. Some providers provide specifications on the basis of which one can build its own implementation. This category includes ARM, where ARM provides the specifications, and one can build some solution on top of that. Another category of this hardware is solutions like Intel and ARM and AMD and so on, and IBM, where they are actually providing complete solutions, complete hardware products on the basis of which one can then use the software on top. So the software category, the third one, is that to facilitate the user who is going to use these confidential computing solutions, the basic idea is that they provide you one-line commands so that you just run your solutions and you don't have to worry about how to build the whole software stack on top of that, on top of the hardware, whether it's ARM or AMD or IBM and something, any of the solutions. So the software category is basically providing these kind of solutions. All right, I will also move this to this side. Okay. Now comes the part of attestation. Why is it important? So the two things that I showed you on the last slide, relying party and the software, hardware, and the application running on top. Let's combine that all together in the form of an attester. So let's call it all together as an attester. That's this thing. And then there is the process of attestation, which is actually bringing you back the guarantees from the cloud. As I said, that the threat model is to remove this cloud provider from the trusted computing base. So the idea, therefore, is that it sends some attestation request. It means that the relying party, and then it gets back an evidence from the cloud provider. And then there is this, after evaluating this evidence, it can send over data or secrets, which are the ones it will send only after confirmation. So that's the whole idea of the attestation mechanism. And we argue here that if this attestation mechanism is removed from confidential computing, it's no longer confidential. Because otherwise all of your data and secrets, if there is no process of this evidence and evidence verification at the relying party end, we have no basis to trust what's going on the cloud provider side. And that's why it's the most important, one of the most important, at least, mechanisms of confidential computing, and which provides you all the guarantees from the hardware up to the software. And this, to just a layman understanding of this whole thing, is just like when we have a process of visa application. And then what happens is that basically we go with our passport, which is our identity. We show our identity. And the visa officer or the border control officer, let's say, he checks the identity that is in the form of a passport or identity card against the reference database that he has. And he checks that everything is correct from that database, that it matches. And then he takes the fingerprints, which in this case of the software code will relate to the hash of the code. So this is very similar to that kind of mechanism, and I will use it as an analogy to understand this whole attestation thing. Right, so moving forward, so the problem statement basically is that we have a number of trusted execution environments, as they are called. They are the hardware products, as I said, which will provide some guarantees. They are called as trusted execution environments. And there are a variety of them. As I said, there are two categories, different categories. One is which is providing only specification, another one which is providing complete products. And in between, there are a number of products. So how do we reason about them mathematically in the form of with an architecture which is agnostic to these trusted execution environments? This is one of the things which is missing and that we were aiming at. And once we have such an architecture that on the basis of which we can analyze it scientifically and mathematically, we need to map these different kind of solutions to this attestation architecture so that we can analyze it. So the mappings do not exist at the moment. And the third problem is that there are no formal specifications of the attestation mechanisms by any of the vendors, whether it's the category of ARM or whether it's the category of Intel and IBM and AMD. So this being the core problem, we wanted to deal with this problem, and now I will describe what approach we took in its essence overall. The idea is very simple. So we have categorized into three main parts that you see here. On the left is the architecture lead solutions, the category that I mentioned, that they provide basically the specifications on the basis of which one can build its own solutions. So the ARM partners, for example, so ARM CCA confidential computing architecture is in this category. They provide the specifications, and ARM's partners can then now build the solutions on top of this, and they can use it according to their specific requirements. So they provide only the specifications. That's why there is a clear boundary between architecture lead solutions and the vendor solutions. The vendor solutions, on the other hand, are basically the complete products. They are providing complete hardware products. And so there is less freedom for moving things around or moving them according to your requirement. Of course, there is some flexibility at the software end, but the hardware product is fixed. Another problem at this end is that some things are actually now hidden. Instead of having some specifications, building implementation on top, meeting these specifications, now it's only one entity, for example, Intel, which is actually providing you all of the product. And we do not have any clear specifications of what exactly is going on inside that product. And in this category, we have Intel SGX, Intel TDX, which is now the updated form of the recent next generation announced solution of Intel. Then we have AMD SEV SNP from AMD, and from IBM, they have announced IBM PEF, which is their solution, and others might be coming up. On the top, we have the frameworks. And relating it back to the figure that I showed on the first slide, hardware and firmware, software, and then our workload. The workload comes from the relying party. Now the software layer, to make the life of the user convenient, there are various frameworks which provide them the software also, so that with one line command, they can actually deal with it, attest everything, get guarantees, and put their workload up to the cloud with all the guarantees. In this category, we have SCONE, Grameen, Microsoft Azure Attestation. Grameen is from Intel, Microsoft Azure Attestation, and Verizon. There is a clear boundary between the two below, but I would say there is not a very clear boundary between when should we say that the architecture lead solutions convert into a framework, or when does the vendor solution convert into a framework actually. So it's kind of a fuzzy thing that whatever the vendor itself is providing is something which is still in the lower category. That's kind of a hardware. And when it's a complete product, it's a framework, but putting a clear boundary that, okay, so this is when exactly it converts into a framework is a bit difficult. So, but this is only a mental map, so to say, to understand that there are different categories. And the core idea here was that to make these categories, probably we can reutilize some of the proofs or some of the work formalizations that we do for one of the solutions in another solution inside this category. For instance, for ARM, if we do some proofs, we can probably use them also for RISC-V trusted execution environments. And similarly, if we do some proofs for Intel TDX, we can probably use some of the material at least for using that for AMD, SAB, SNP. So this was the core idea, that we have categorized them to understand them better in this framework. And we provide, our approach is basically that we do provide the formalizations for ARM CCA in this category, Intel TDX, which is the next generation solution from Intel in this category, and SCONE as the frameworks in the upper category. So that's the basic idea of the thing. And this figure is describing how the overall approach works. The basic core idea I described already: architecture lead solutions, vendor solutions, and frameworks. This is kind of showing how the connections actually work, or how do we use these to build the solution and formalization going up to the formal proof. So the core idea is that we have one of these two solutions. As I said, we take ARM CCA in this category, Intel TDX in this category, frameworks built on top of them, which means that it can take either solutions from this category, or it can take from this category, or a combination of both. So frameworks may also support multiple trusted execution environments from within the same category or from different categories. Frameworks are supposed to be TE agnostic, so people can use the same framework for different TEs. So any of these three solutions or frameworks can be input to this TE agnostic attestation architecture-based specifications. And the advantage here of the TE agnostic is that it will deal with it. It can be used to specify whichever TE is given to it as an input. So the term agnostic. And what happens inside these specifications, or what exactly is specified in this, is basically three things, or three phases, so to say, of the attestation mechanism. Provisioning, starting from the point when it was manufactured by the manufacturer, embedded some secret into the device, and going up to the process of being put into the cloud, which is the attestation protocol, which I described that it will do when a relying party will connect to the workload in the cloud. And in between, there is a process of initialization, which are some setup phase, some one-time initialization steps which are taken by the cloud provider. And these specifications can now be given to the formal model can be created from these specifications, which basically means that, and on the basis of that formal model, we can then reason about the security guarantees of these attestation mechanisms. So these will be analyzed via properties, as you know, and then for formal model, of course, we need some assumptions, and that's not actually a drawback of the approach. I would say that's the key outcome of the approach, that basically we know what exactly assumptions are being required for the proof to work, and the implementation has to satisfy these specific assumptions. So that's also a key insight inside this formal proof, to know exactly what assumptions should hold for our model to work in providing these guarantees. Right. So this is as I said, the approach combines these two things, which are this T-agnostic architecture and formal analysis. Formal analysis, of course, is very common, and you guys are also experts in all this, as I assume all of you use this, or at least have some familiarity with it. The idea is that, so this thing already exists. This thing we created, made it T-agnostic, as I will describe. But on this slide, I just want to give you a core idea of what's the benefit of combination of this, or why we need to have both together. Formal analysis, I hope you are all convinced that we actually need to formalize these systems. As I said, this is important because all my secrets and data will be at stake if I do not have any guarantees. So it's a critical process. We need formal analysis, but what's the use of these specifications? The core idea is that if we have a T-agnostic, every vendor, independent of this, whether this is architecture, lead solution, vendor solution, or framework, can map their specifications to this. So it's actually, we do provide for one of these, one of the three for each category. But this is actually meant to be that the vendors will use this to map their solutions to this specifications. So they use it to specify that. And then the verification engineer has an easier life of doing the verification and providing the guarantees, instead of understanding each and every terminology. AMD, SCV, SNB, let's say, uses this term for that. Intel uses this term for that. So to remove the barrier of the different terminologies, and other than that, other than having the life of the verification engineer easier, it's also important to actually compare these two solutions. What terminology Intel uses and AMD uses, how do we compare and contrast them and reason about them? That's also important. So that's why we have both steps or both specifications. And the motivation is that this part is assumed to be provided by the vendors themselves. And then this part, the verification engineer can then take and understand these specifications and then utilize them to build and verify that. So it will be easier for him to verify. Okay. Any questions so far? Is it clear? Or yes, please.
Yes. So I mean, this is the overview, and it's clear that some of the systems from Intel correspond approximately to certain things in RISC-V and so on. But how much commonality is there in practice between SGX and ARM confidential compute for Fossati? Are they in fact providing similar things?
Okay, so you mean actually across the categories, right? Vendor solutions versus architecture lead solutions.
Well,
is this
within them? I mean,
within them.
ARM CCA
Right.
has multiple different things. Is there do frameworks plausibly use them generically and are agnostic to it, or how much in practice do they have to be custom built for each one?
Right. So this I will the architecture itself, I will describe that it's completely agnostic to the definitions, at least that we can understand them, what are the references and reference values, endorsements, and so on. So there is some terminology involved. I would say at a high level, to understand them, one can reason about that, because in terms of commonality, all of them have measurements that it measures, that needs a root of trust for measurement. That's common inside, whether it's architecture or vendor solution. That we need measurement is one of the most important things for attestation. They have different kinds. They have different root of trust, but then also one needs to analyze what is the TCB of the system. This architecture will help them understand what the TCB is. From commonalities, at least I see that the measurements are done in any of the solutions.
Okay,
That's
so they
that's
provide
common.
similar facilities, perhaps in different ways.
Yeah, exactly.
Okay.
So it's kind of providing the measurements in, I would say, the category of ARM is providing you more flexibility, so to say, that it provides you specifications. I can build a solution on top of that. Or let's say ARM partners can build on that. But the basic requirement of confidential computing is still the same, that it's to remove the cloud provider from the TCP. Okay, so anything else from anyone here so far? Okay, good. So let's proceed with the contributions. I described the problem statement and some motivation and high-level overview of the approach, why we need the combination of both specifications, how does it help. Let's talk about the contributions specifically, which is exactly what the question was related to. So we have the first one, which is T-agnostic architecture. There is a group called, there's a working group of IETF called Remote Attestation Procedures, RATS working group. They have over the 5 years come up with an attestation architecture, and that's standardized now. This is this RFC 9334. But there are a couple of limitations, important limitations from the practical perspectives of the TEs. The first one being that it cannot express anonymous attestation, which is that the attester would like to be, it's in a group and one cannot identify which specific attester has generated this evidence. And it's important, as I said, practically, because Intel's attestation mechanism, which is called Enhanced Privacy Identification, EPID, is actually one of the solutions for attestation, which is anonymous, and that standard cannot represent this. Second and more important thing is that all of attestation mechanisms of Intel are actually based on the fact that there is a local attestation going on, and then the remote attestation is just doing a signature and sending over to the remote party. So local attestation there is actually a core part of the remote attestation. You cannot do remote attestation without doing local attestation first. However, the standard actually focuses on the remote attestation and eliminates local attestation at all. So these are the two main limitations. Otherwise, there are a number of ambiguities also within the attestation architecture. It's not clear what is the reference values, difference between the reference values and endorsements. There are a number of other ambiguities. So what we did is that we have submitted the errata for this standard. And there is some follow-up work going on. There is a new draft which has emerged based on that. Endorsements versus reference values, Dave Taylor and so on are actually working on that to clarify the standard actually. So what we propose here is this attestation architecture. And there are a number of terms, but I would like to simplify it a little bit. Attester, coming back to the example of the analogy of the user, border control officer, and the government. So basically, this guy here, let's assume, is the one which is going to pass the border control, and this verifier is actually the border control officer. And the third one, the relying party here, is the government who has appointed that border control officer. So the government actually wants that the security of their country, of course, and in order to maintain that nobody who is, let's say, a threat to the country crosses the border and comes to their country to create something bad. And they have delegated it to the verifier, that is the border control officer, to check everything, that everybody who passes the border control goes through some checks or some policies, so to say, which is actually the word here. So based on these policies or the rules or the regulations which are given to him by somebody, he will be checking that everything that the person is stating is correct. And that basically he checks against some database that is available to him. For instance, firstly, the passport or the identity card. what he will do is he will scan it and he will check that it's valid, it's not being forged, and it's not fake, and so on. And that's basically against the database that he has, kind of these reference values. Secondly, he will check the fingerprints. If you have an experience of passing through this border control in Europe, of course, we can move around. But if you had a chance to, let's say, to US or some other country where you had to cross the border and go through the pass. So they also take sometimes the fingerprints. And that's really equivalent to or analogous to what we have here as the hash of the code. That is, the fingerprint is my identity, and he has in his database all the fingerprints matched to each person's identity, which are, let's say, taken at some other point of time. That can be some, when I registered for my passport, at that point of time, I gave the fingerprints and they have now stored it for that. Or when I applied for the visa, I gave some fingerprints that now they have it in their database. They can correspond it that is it a valid signature, is it a valid fingerprint or not. So this is the kind of analogy to understand what's going on inside this process, and that fingerprints basically represent the hash of the code that I can check, or the verifier can now check that whatever the attester is presenting as an evidence in the form of a passport, or let's say the fingerprints, actually matches what he has from the database as in the reference values and the appraisal policy, which is given by the government or given by the verifier owner, that it follows all the policies. Let's say the business that this person is going to do is valid and is genuine. And there is, as I said, there is an ambiguity between what exactly is the difference between endorsements and reference values. In the draft and the standard, what we propose here is that basically endorsements are the certificates and the certificate revocation lists. So we specify that like this. And the measurements and all other things, the hashes and so on, basically they are the reference values. So this is one clear way of distinguishing that. Secondly, there was this local attestation, as I said, the limitation of the standard. What we did here was that we added the prefixes to these terms. So when we say, let's say, an evidence, local evidence versus a remote evidence, to distinguish between whether it was local to the platform or remote to the platform. So very easy, just by clarifying the context we are talking about, adding the prefix, we can clearly distinguish what we are talking about. And about anonymous attestation, we add here one specific rule, which is this identity supplier. And this is this can be the manufacturer at the time of manufacturing, where they embed this identity in the form of fuses and so on to the device that is this attester. And that's with that we can now analyze also the anonymous attestation in addition to other forms of attestation. So we claim that this is TE agnostic, whichever TEE we have, whether it's from the first category or the second category, we can reason about this at an abstract way, and it's clear enough for the vendors after the mapping that I will show you, that with this mapping it should serve them as a sample for them, or as an inspiration for them to how to specify their specifications, their documents. As I will show, they have done it very poorly so far, so that was the motivation of this thing. Okay, now we have T agnostic architecture, or at least we have some inspiration of that. How do we map them? How do we map the real world TEs to this attestation architecture? And here I will describe the need of that. There are a few works who have attempted to do this kind of mapping, which is this IETF RATS working group. I just described the standard. academic effort by Ministry et al. And this is also the last one is an industrial effort, Nimi et al. From Huawei. So the architecture that they use is, in the first case, this was developed with or co-developed with DICE. And the second one uses RATS architecture. And the third one adapt the RATS architecture a little bit. Coming to the mappings, defining them for each group. Specifically, the first two do not have any mapping for the group one, which is this ARM CCA group, where you have all the flexibility or the specifications from the vendors. And the third one actually provide for ARM CCA, but it's a very high level summary. They do not describe it in detail what's going on. So it's just very high level initial summary of the thing. In the second category of Intel SGX, TDX, AMD, and so on, the first work does not provide any mapping. And the second one actually provides a mapping for SGX, but it's in fact, unfortunately, inaccurate at various points. Like they define, they say that, or they claim that they use RATS architecture, but unfortunately, when they use the term attester, as I described in the last slide, they use it in a conflicting meaning as opposed to what the architecture, what the standard says. We have various examples of the inaccuracies in our draft, and I will be happy to return to this if you have questions. For the SGX category, again, this is very high level, and they do not describe even that which attestation mechanisms they have actually presented in the paper. Like they are APID and DCAP, the two main attestation of SGX. And they don't even, it's from the paper, it's not even clear whether they are describing APID or whether they are describing DCAP. And that's why we claim that it's very high level. And in the third category of the frameworks, nobody has analyzed it so far. And that's our first work, which is describing the mappings to the complete frameworks and analyzing them formally. Right, so a lot of details here. I will not go to the details. The idea here is to just show how do the mappings look like. So it's very easy. The thing is that with these dotted lines, we represent the role, and with these solid lines, we represent the entities which take on these roles. So there is a role of the, let's say, coming back to the analogy of the border control officer. There is one specific border control officer, let's say at this point of time, and his duty, let's say, ends at 6 p.m. Another border control officer comes and takes on that role. And then there are people, different people coming in that in our analogy were the attesters, different people coming in from different flights, passing through this border control. And then he keeps checking, and after some point of time, his duty will finish and somebody else will take that role. So simply the concept is to differentiate between the entities and the roles. We describe this dotted lines to represent the target environment. And the realm instance in this case is the entity which is taking on the role of the target environment. And so on for other entities that you see in this diagram. We have all the, for example, RMM taking on the attesting environment role. And here the monitor security domain taking up the role of the target environment, and HES taking on the attesting environment role. So it's very clear that which entity takes on a specific role from that RATS architecture, which I just described. And at the end, as I said, there's this remote evidence versus local evidence, which distinguishes whether we are talking about remote attestation or local attestation. And this goes to the verifier. So that's the idea of how do we describe the mappings. For ARM, it's a bit easy. For Intel, it's a bit more complicated. If you have any questions until now, feel free to put it now. Otherwise, I can talk about the formal specs next. Okay, clear. So let's go to the formal specs. The third contribution that I said that there are no formal specifications in any of the categories. People have bunch of codes, bunch of specification documents, as they call it, but that does not specify exactly what's going on. So what we do is we have, again, the same analogy, same description. The dotted lines represent the roles, and then the solid lines represent the entity which takes up this role, the RAT's roles. And then we have this attestation protocol. What happens is verifier sends a challenge, and this target environment forwards this attestation request, including this challenge. And then it creates some claims. The testing environment creates some claims about the target environment and includes the challenge as well as the public of this key, that is the RAK. And then it signs the claim set using the RAK, and that creates basically a REN evidence. And there is also one platform evidence that it gets in the initial phase, the initialization phase. So this is just one part of the protocol. From the initialization phase, it has obtained the platform evidence, and it combines the two evidence, sends back to the target environment, and the target environment basically forwards it to the verifier. And this whole thing basically combined together is the remote evidence. So this leads to a better understanding of step by step what exactly is happening and what should be signed, what are the claims, and so on. It only says claim set, but there is a description in the paper that what exactly these claim sets are. Right, so for doing the formal analysis, we don't only need a model, we also need some assumptions. And with these assumptions, we can prove some properties. And there is a tool called ProVerif, which is very good at doing that for cryptographic protocols. It can prove properties for unbounded number of protocol sessions, and it's basically based on applied pi calculus. In the next slide, I have some description of what goes on inside the architecture of ProVerif. But for this formal specifications, I just want to describe for ARM CCA what happens. For instance, the assumptions are that the verifier has pre-configured public part of the key CPAK for signature verification. And secondly, that the secure channel between the two entities, HES and RMM, is already established to transport the RAK key pair. And the properties that we then prove are the integrity properties of the platform and REN evidence. And it is of this form in ProVerif. We have a query with the claims, and it's of type bit string. And we place the events which are not, which do not add anything to the knowledge of the adversary. And these events are then placed as at the point, the accepted event is placed at the point when the event, when the evidence was accepted, that it's genuine. And the sent event is placed at the point when the sender sent its message. So this query will then check actually that the claims which were in the sent event are the same as what was received at the acceptor verifier or the receiver, and they should be the same. So if they are the same, then this query will be verified. And the second thing is that the injectivity here, the injective event basically in ProVerif means that there is a one-to-one correspondence, meaning that it also checks the freshness of the thing, that the claims are freshly generated by using that norms. Okay, so I want to now quickly describe about how the approach works inside ProVerif. We have a system configuration and operational policies extracted from the architecture documents of any of these TEs, and from that we build the symbolic model. Security goals represented as security properties, just like the one I showed on the last slide, formalized in the ProVerif specification language. This is also in Proverif specification language, the symbolic model applied by calculus. And Proverif inside, so this part is that what we have to model, and now this part is done automatically by Proverif. Proverif automatically translated to the horn clauses and then tries to resolve them. In case the fact is derivable from these horn clauses, it tries to reconstruct the attack at this applied pi calculus level. And now there are, so this dotted box represents what happens inside Proverif automatically. And now there are two possibilities that the attack reconstruction can either be successful or not successful. If this is successful, we have successfully found an attack, that is the property is false. For this property is false for this specific model. And we then can analyze that, how to fix this attack. Proverif is not complete. It could also happen that attack, so the horn clauses level, it resolves, but unfortunately at the applied pi calculus, it cannot resolve the attack back. And then in that case, we have an answer of don't know. And then we have to see the horn clauses. And the third possibility here is that the fact is not derivable at the horn clause level. In that case, the property is true. That is, the system model or the symbolic model that we created satisfies this specific security property. So this is the core of how the Proverif tool inside works, starting from applied pi calculus modeling, up to the these answers that whether the security property holds or not. Okay, so then I will switch quickly to the demo for a short one, maybe. Sorry, 5 to 10 minutes. Okay, yeah, sure. Okay, so this is the model I have for TDX specifically, and here it's trying to translate the process into horn clauses. And while it does check 4 to 5 properties which I have, I will describe you a little bit about the model itself. For instance, here I have all the assumptions which I needed. The assumptions that I described on the slide were for ARM CCA. So this is the other category, Intel TDX. The secure channels that I need for between the different entities are described here. And this is also one secure channel. And one thing that we use for giving adversary the power to create different TDs is that we allow it to create any fake TD and get its code. However, to model this, what we do is that all claims are with the corresponding reference values are obtained from the adversary. That is, and we will take as an input from the adversary these measurements, and the verifier will then match and check the fingerprints. Again, the border control officer example. It will check the measurements and check the fingerprints and accept the person only if the fingerprints match to the original ones or one specific ones corresponding to that. Okay, so with these assumptions, we have these are the initialization steps. As I said, there are 3 different phases: provisioning, the point at which the hardware was injected with the secret; initialization phase, these 7 steps; and then attestation protocol phase. These steps are described here. And at the end, we have a secret sent over from the verifier to the TD, which is actually this step, 20th, encrypted with the public key of the TDK. This is the secret, and what we want to check is that the TD can actually decrypt this secret, and the secret is not available to the adversary. So this is the secrecy property that we check at the end of the protocol. And other than that, there is this property of Okay, so I will quickly move to. All right, so we check some reachability properties that the events inside the protocol are reachable. CPU sent SMR, for instance, TDX M sent TDR, that the protocol actually reaches this point of in the protocol. And then we have this quote verified. This is important to check that the quote, at least there is one reachable state where the quote was actually verified. So this is the evidence that the relying part that was sent by the attester. So the quote is verified. If the quote is verified, that is this is if the quote verified event is reachable, then one can also check that the integrity property is similar to the one that I described for ARM CCA. In this case, there are TCPI claims, TDI claims, and R data, a specific user-defined field. So this specific query checks that the TCPI claims and R data fields for the event when the CPU created this SMR is a specific report, SEAM report. Then from that step up to the point when the quote was verified at the verifier end, remote attestation, the values are passing through the adversary, including the VMM and so on, cannot be, are preserved, are not changed. That is the integrity of the thing. And then for the TDI claims, so this property was for the TCPI claims, and sorry, I think this. Okay, so this property was for the TCPI claims, and the one I show now is for the TDI claims, that when the TDX module is the entity which generates this TD report, and this event is exactly at the point when it was generated. So again, the same concept from generation up to the code verification, there was no change in the TDI claims. So this describes, and then this is the secrecy property, signal 19 property. ProVerif takes care of everything inside. The main challenge is how to find out the model. By the time now we have everything finished by ProVerif. And the verification summary is like this, that this event is false, which is not of this event is false, which means that this is reachable. Not of this event is also false, this is also reachable, this is also reachable, so everything is fine. So the protocol actually has some path to this. And then this is the integrity property, that the TCPI claims and R data 1 remain same from the send point up to the verification point. The property is true, and it's injective event, so that is with freshness. And the TDI claims starting from this point up to the verification, up to the port verification point is maintained, and not of attacker is secret is true, which means that the secrecy is preserved. So this is ProVerif's way of saying that. If there are any questions, you can ask now. Otherwise, I switch back to the slide quickly to describe some challenges. Okay, so all right. So the challenges, and then I will finish. I don't have to cover all the slides. So this is, I will give you, and then if you have questions, I will be very happy to discuss. Specifically for TDX, it was really complex. As I said, this category has a complete product. Nothing is clear about what exactly is going on inside the solutions. There are 1,500 pages of the specifications of TDX. In addition, it's using many things from SGX, its previous solution, previous trusted execution environment of Intel. And the software development manual itself alone is of 5,000 pages. Specifications are all in natural language. One does not know what exactly is basically signed, what exactly is sent over to this party, and then it's all a mess. And another challenge is how do we model the adversary powers at the symbolic level in a clear way. Okay, because there are a number of limitations that I have next, but and then for the frameworks perspective, there is the challenge was that that's the closed source nature of SCONE. So it's not available. Many specifications we had to find out by discussion with the developers. Okay, so I can jump to conclusion, or I can give at least one design security issue. Is that fine?
We should wrap up.
Okay, let's okay, then I go to this. All right, so T agnostic approach is comprehensive specifications and formal analysis, combining the both together, taking the benefit of the formal analysis and its properties. Also, with the help of the T agnostic architecture, it makes it comprehensive, that we have not missed any cases. As I said, the standard was developed over 5 years. It has a lot of depths, and we still want to utilize that standard, not to throw away the whole work of 5 years that the industrials have done. For TDX, how do we precisely express the trust boundaries, as it's not clear? And for SCONE, when exactly do we say that something is attested? So this was one part of the security issues that I skipped. And what we are heading towards is basically a T agnostic verification infrastructure. Sorry, for transparency and interoperability. As I said, these organizations are not revealing many of the important details that we think, or we strongly believe are very important for analysis. And that's why verification infrastructure, such an infrastructure, will help people understand not only that how it actually works, but also help the developers that how do they need to develop these solutions and to utilize them better. In that regard, we are working with ARM on the integration of remote attestation with TLS, RATLS. This is one ongoing project, and also in cooperation with Barkhausen Institute. And we are working also with the Intel to integrate the VTPM solution and formally verify this VTPM solution with the trust domain, the user trust domain. These are the key references, and a quick call to action. We have this repo where we will have the TDX artifacts within 2 weeks. This was recently accepted project of CCC Attestation, and under a very generous license, Apache license 2.0. So you are free to utilize that, and we invite you to bring your verification expertise and to further build on that and move it forward. Additional information is available on this link. That's the link to the paper, which you might have from the abstract also. And we are organizing the 3rd version of PAVE Trust with this conference, ACSAC in Austin in December. We have basically the core idea is the works on the intersection of formal methods and trusted hardware. So if you have something in relation to this, we would very much welcome this. And if you are also interested in speaking as a keynote speaker, please do discuss with me. We can fund your travel to Austin and visa and all the things. We will take care of everything. Thank you very much for this opportunity, and I am very happy to take questions from your side.
So, question about you illustrated the program operation structure, and in particular that if you have a failure to do something like it, generate counterexamples or attacks. Has that path actually happened?
Yes, you mean that when the property was not true, and then then to analyze that counterexample, right? Yes, yeah, that's true. When there is when the property is false, it gives a counterexample. It also gives a nice trace of the property. How does it where exactly did it fail? For instance, for the secrecy property, it will show you a trace where the attacker running in parallel to the protocol in any of the sessions. Of course, there are unbounded number of sessions, so it can create multiple of these, take information from one to put into another, and then it shows that what actually was happening there to understand better and to fix the protocol.
Okay, and have you had instances this arise where?
Yeah, exactly. So we had many instances where it was actually, as I said, the protocol was in natural language. So this data is signed and sent over to this, and that is done like this. So I would argue actually, which I did not mention in the talk, but it was not only a verification problem, it was, I would argue, it was a design problem basically.
No, I mean,
because
when it get a fall, then clearly it might be the specification, it might be implementation, it could be, it's generally a mismatch. It's
yeah,
unclear which one is wrong.
Yeah, exactly.
Was that protocol actually deployed before the was discovered? Was this that we're actually find something before they actually align this?
Are you talking about the property failed, or I didn't quite get the
so you've come across problems with protocols before, and
problems of?
so you came across these failures of storage properties.
Yeah, right.
Was the protocol actually deployed at that point, or did you
no, the TDX protocol actually is not yet deployed. So we had this draft roughly in December, when we were finished in December. So by that time, TDX protocol was only in the specifications. It was specification documents which were available. Now, I think there are some cloud providers, including Microsoft, have announced some preview version of TDX, but we do not have the hardware available to test and verify on the hardware actually. So we went through all of the documents of TDX, we analyzed that, and from our previous knowledge of SGX, which we have done in our previous work, and the expertise of the ARM guys for the ARM CCA, we actually built the models from our understanding of how the protocols should work.
How easy is it to tell vendors and protocols correctly?
Push calls? I'm not sure.
How easy is it to tell that a vendor has correctly implemented the protocol? Obviously, if you actually get the end of it, they identify it. Is it if you're a cloud provider, you're buying solutions, so that you can do attestation.
Yeah.
And you have some visibility of the product you're buying. Can you be certain that this actually functions fully, and that you won't discover that your customers are complaining to you because the attestation protocol hasn't worked? They've got faulty evidence that it's being rejected. I'm sure that's very clear.
Was that a question or a comment? I'm not sure.
So the scenario I'm thinking of is that you're a cloud provider.
Yeah.
You're buying some product which uses the attestation protocol.
Right. So let's make it fixed. So let's say the cloud provider is, let's say, Microsoft.
Yeah.
And it's providing some TE, which is, let's say, Intel TDX, right?
Right. And the what's in the machinery for doing attestation from someone.
Right. So what do you mean by
that person has actually implemented the protocol properly, so that they know that every time their customers connect to the cloud, they will get the proper attestation.
Okay, so when you say that they have got the machinery for attestation, so I just want to clarify this. So there is one part of it is related to the hardware, and another part of it is related to the software. So the thing is that this part mostly deals with the hardware part, and frameworks are building on top of that, the software part, the software layer, or It's more related to the verification of the evidence. And this is actually the hardware is generating the evidence. So when you say the machinery of the attestation, does it relate more to this or to
I think it's mostly frameworks.
frameworks? Okay. Okay. So you have then this kind of scenario where you have someone providing you the software, the hardware provided by Intel, let's say, and this provided by the cloud providers, let's say Microsoft. And now, what would be your question?
My worry would be the software has faults in it.
Software has fault in it. Okay, right.
So eventually the protocol will fail and shut down.
Okay. Oh yes, this is absolutely correct. So this is a part of the TCB. If I have taken some solution from some software provider, I probably forgot this when I was discussing, I was presenting, because I colored them differently, if you notice, because I was to say that this is trusted in any case. If I take that the hardware provider is always trusted, I can either build my own attestation framework. In that case, I don't need to trust somebody. But if I take third-party framework for software, for example, SCONE or any of these upper layer frameworks, I absolutely have to trust them that they are doing the job correctly. So it's in the TCB. No, the cloud provider is the third entity, which is this. So this software corresponds to this layer of framework. So this is, for example, SCONE providing the facilities, which is different from the cloud provider, which can be Microsoft Azure. And then this is software provider, and that is the cloud provider.
Also, now that you have a size specification of what, or you have a size specification, price description of what the specification is supposed to be, does that then enable you to check such implementations either by historical or fuzzy or somehow run against them to confirm they do the right thing? Because you don't have a precise model of what the right thing is. You'll be able to compare it given a supposed implementation.
Just to clarify, so your question is about this interaction between the two.
The situation Brian described, you've got this piece of software which is supposed to implement.
Okay. So this is a follow-up to this question, right?
Yeah.
So this is that the software provider has some problem.
Well,
and
so you have some software, and you don't have one just a big manual. You don't have a precise specification of what you want that software to do.
Right.
And does that help with checking whether the software or testing the software to see if it does it? And obviously, you could just deploy it and wait for complaints to come in that it's not certified.
Yeah.
But even that you have a precise description, can you use that to exercise the software, explore the possible paths?
Yes, theoretically it would be possible if we have not this limitation of where did I put it? So I think somewhere I was describing the limitations of this one, closed source nature of SCONE. If I have that actually the software with me, and I have these precise specifications, I can actually then verify that's very much possible.
So I'm talking about more about necessarily black box testing.
Okay.
You have a precise machine that has done a model of what its response should be in all circumstances.
That's a good idea. We haven't explored that, but I think that's a good direction. That would be one way of doing that, because if we don't have the code, we have to rely on such methods to at least check them, rather than just blindly trusting them. We can actually test via different methods like the ones you described. Yes, please.
So we're talking a bit about modeling of the attackers, and we have in the literature a lot of different ways to break attestation protocols. How does that fit within the modeling? Can you model? Can you do that? Yeah, you try modeling and existing attacks.
So if you talk about specifically about attestation, so our work is very focused on attestation in confidential computing.
Right. Yeah, but within confidential computing, there's already quite a few attacks, and some of it is
attacks. Okay. So
some of this specific hardware offers.
Yeah. So I absolutely agree. There are a number of attacks, SGAXE and so on. There have been a number of attacks on that. But our protocol, so our verification is very focused on firstly the attestation mechanisms. So that's pretty much it that we claim. We do not check the other things, or other attacks are actually out of context. And for instance, we have only the fingerprints representing the code, so we do not look into that. So it's symbolic approach. So attacks like that cannot be dealt with and cannot be found using this. So it can only find the attacks which are protocol related, that the protocol is faulty. And from that perspective, the only thing that comes to my mind is fork attacks. And we are analyzing that currently, but I am not aware of any other effort which has actually formally analyzed that. There is one work which is going on at the University of Zagreb, Ante Derek. He's working on AMD, SCV, and Intel SCX attestation combined protocol. And they are also working on AMD, SCV, SNP, where they have in the category of, let me quickly show you in the category where that is. In this category, basically, what we did was Intel SCX TDX, and they are working on this AMD, SCV, SNP, and that's kind of a complementary work to ours. We have not done any work with AMD. And just last week, he was actually presenting the work to our group, and they haven't found any attack on the system. So they have verified the AMD and SGX combination of protocols. So formally speaking, I am not aware of any works which have actually, other than University of Zagreb, Ante Derek, I'm not aware of any body who has formally analyzed these attestation mechanisms. So at least currently there is no current work on the verification.
So all the breach attacks are kind of like a combination of like physical attacks.
Yeah, there are other attacks, not related to attestation.
Okay. But they cause attestation to break because
they cause attestation to break, actually. Yeah. So if one of the keys leaked, for example, in SCX, SCAXE, as it was named, so the attestation key is leaked, and then it leads to attestation, like you can sign fake attestations. And that's why the core motivation was to understand the mechanisms better and to build them better. In some of the slides that I skipped, I will just quickly show that this is the certificate chain that was never described in any of Intel's documentation. And our goal is then to build and understand the code, build the models precisely, understand, and we have also optimized it a lot, and building the things in the proper way, where when we discuss with the Intel guys, they actually themselves are not clear because it's so complex, it's getting so complex that nobody actually understands them. So there is a lot of detail inside that, and we are trying our best to include as many details as possible. Yeah, and we are very happy to have your expertise also. In, as I said, in 2 weeks we will be pushing that code basis to the CCC repo.